Leeds, talking on fermionic quantization of not solitons.
Okay, thank you very much. So thanks to the organisers for inviting me. Thanks to Paul Sutcliffe for buggering off and not being present. But anyway, So my talk is on fermionic quantization of not solitons. So these are, I'm calling them not solitons. They're the same solitons that Derek was just talking about, in fact. So let's have a quick reminder of what the model is that we're talking about. So I want to be a little bit more general than Derek was. I want to think about these things on a general oriented three-manifold, M3. So a Riemannian oriented three-manifold. So we have a map phi from a three-manifold M into S2, and given such a map, we can define an energy in this way. So it has two terms: the Dirichlet energy term, familiar from harmonic maps. That's the thing that was quadratic in derivatives. And then we have a thing which is quartic in derivatives, which is a really nice way to think of this term. This is the thing that had sort of vector products in Derek's presentation. Think about the standard area form on the unit 2 sphere. That's a 2 form. Take its pullback by phi, that's a 2 form on M3. Take its length squared. In other words, wedge it with its Hodge dual and integrate over M. Okay? So this is a very nice natural energy functional to write down when you're thinking about maps from a 3-manifold into a 2 sphere. It was first written down by Fadeev in the 70s. And it's nice because it has this quadratic quartic balance in dimension 3, so these two terms scale inversely when you squeeze a configuration, and that's what's allowing stable solitons to arise. Okay, so about the topology. So we all know that at least if M3 is the 3-sphere, or R3 with a point out at infinity to capture a boundary condition, pi 3 of S2 is Z. So there's some non-trivial homotopy here. What is the homotopy? Well, one way to think of it is as following. You pick a regular value of this map. So a map, a value, all of it, such as that the differential at every point which gets mapped to that value has maximal rank, has rank 2. Then, if you look at the pre-image of a regular value, you're guaranteed to get a closed curve. Okay, and this is what people call the knot. What I want to point out actually is that this is a bit of a misnomer. Okay, these things are not really, they're called not solitons, but the knot is really of no topological significance. Okay, what is of topological significance is the framed cobordism class of that knot. Okay, so what am I saying here? So here if M3 is R3, I'm imposing this boundary condition at infinity. So the thing which is a homotopy invariant of this map is the framed cobordism class of this framed link. Okay, so you pick an oriented basis at this point here, this in the target space, that gives you a framing. It gives you a basis for the normal space at each point of this pre-image curve, and actually the thing which is a homotopy invariant of this map, which doesn't change under continuous deformations, is the framed cobordism class of that thing. Okay. So to call them not solitons is a slightly misleading thing, but of course it gets you invited to conferences like this, so I'm not complaining. Okay, so that's a geometric picture of how you classify these things homotopically when you're mapping from a compact oriented 3-manifold into S2. Is there an algebraic way of doing it? Well, there is, and there is a link between the two. It's rather subtle, in fact. It was first discovered by Pontryagin in 1941. So if you want to classify maps from a compact oriented 3-manifold into S2 up to homotopy, then you find that the class of maps fall into families, which are labeled by an element of the second cohomology group of M. Okay, and what that is, you just take the generator. So the second cohomology of S2 is just Z, so it has a generator. You have a choice of 2. Choose one, call that mu S2. So if you like, think of this as just being an area form normalized so the total area is 1. Okay, if you want to think in terms of de Rham cohomology. You can take the pullback of that, which is a 2 cohomology class on M3. Okay, and for each one of those in H2 of MZ, you have a family of homotopy classes. Okay, so what does that correspond to? Well, it's a 2 cohomology class in here, so it has a Poincare dual, which is a 1 cycle in M3, and that's the pre-image curve, right? It's the homology class of the pre-image curve. So that bit's reasonably straightforward. What's not so the thing which captures the framing is not so straightforward. Okay, so the families fall into the classes fall into families labelled by that homotopy invariant, and then within the alpha class, the individual classes within the alpha family, are labelled by elements of this: the quotient of the third cohomology group by a subgroup of the third cohomology group, given by wedging H1, the first cohomology group, with twice this thing labelling the family. Okay. So as you can see, and this somehow is telling you about the framing. So as you can see, it's in general, this is a bit more. It's a bit more sophisticated than one's used to dealing with when we're doing topological solitons. Okay, so I want to talk about the topology of the configuration space of this model, the topology of the space of maps from M3 into S2. And to do that, I'm going to need some notation. So the standard notation for the space of maps from X to Y, where I choose base points, is Y to the power X. A bit odd, but it is standard. So let's adopt that convention. Y to the X means the space of continuous maps from X to Y, given the compact open topology. Okay, so it's a nice topological space. So in the case where X is a compact oriented 3 manifold and Y is S2, that's the space. That's the configuration space of the Fadeev-Skirm model. As I said, this has disjoint components, and the components fall into families labelled by this thing alpha, the pullback of the generator of the second cohomology of S2. Right. So there's one particular family which is nice and physically meaningful, and that I want to think about pretty much exclusively, and that's called the algebraically inessential family. So these are the ones where the pullback of the generator of the second cohomology is trivial. Okay. So this is one family of classes sitting inside this set of classes. Okay. So they're labelled. If you remember what the theorem said, within the alpha class. Within the alpha family, the classes are labelled by this. If alpha is 0, they're just labelled by H3, right? So the classes, the homotopy classes in the algebraically inessential family are just labelled by H3 of MZ. Since we're in a compact oriented 3 manifold, that's just that. Okay. So there is just an integer topological invariant, at least for maps, for algebraically inessential maps. So in particular, if H2 is 0, remember we got H3 and we divided it by 2 alpha cup H1, where alpha was in H2. If H2 is trivial, everything's algebraically inessential, right? Right. So this thing is bound to be 0 if H2 is 0, and then we're always just labelling things by H3. Okay. So in particular, this is true in the case of most interest, where our domain is the 3 sphere, thought of as being R3 with a space with a point at infinity to capture the boundary condition. In this case, so if you're dealing with the algebraically inessential family, then there's a nice, things are labelled, the homotopy class is labelled by an integer, and there is a nice integral formula that you can write down. Since the pullback of, say, the normalized area form is cohomologically trivial, you can write it as the exterior derivative of a 1 form, and then you can compute this. Okay, so that's the usual way of writing down the Hopf degree. Okay. So I'm going to talk about algebraically inessential maps. I'm not really going to talk about essential maps at all. One excuse for not doing that is if you think about essential maps, that's when this class here is non-trivial. That means the Poincaré dual of that is non-trivial. So that means that these pre-image curves are wrapping around a non-trivial 1 cycle in the domain. So that the structure of the soliton is somehow tied to a topological structure in the domain. So that I don't regard those as being really physically localized particles. They're sort of tied to a special feature of the domain. So they're like topological geons. Okay. So you've already seen this picture. This is numerics by Batty and Sutcliffe. So in R3, with the appropriate boundary condition, if you look for numerical energy minimizers, this is what the pre-image curves look like. Okay, so these things are called knot solitons. I've already told you I don't think they're really knots, because homotopically what's important is the framed cobordism class, or the framed link, not its isotopic class. You could ask actually, are they solitons? Because the ons at the end of solitons is supposed to mean that they're particle-like. Well, they're spatially localized and smooth and have localized energy, but on the other hand, they seem to have string-like structure, okay, which is a bit strange for a soliton. It's not really very particle-like. The other thing is, at least on R3, their energy grows like q to the power 3/4, which again is not very particle-like. Usually, the energy of a collection of q particles should go roughly like q. Right? Now, actually, if you're on a compact domain, E does go like q. Not like q, but anyway. So this is sort of not very particle-like. What else? What other particle-like features could we ask for? Well, one thing that you can do with point particles is you have a choice. You can either quantize them as fermions or as bosons. So you'd like to be able to quantize these things as fermions. Okay? So can we? Well, this is really a question about the space of maps from M to S2. Okay? So how do you quantize a field theory? Naively, you think about writing down a wave function on the field configuration space. So let's call the charge Q part of the space of maps from M to S2 CQ. So this is the charge Q part of the configuration space. So in naive quantization, you just write down a wave function on that thing, or you imagine writing down a wave function on that thing. Now, in this situation, that's inherently bosonic, because if you've got a Hopfion here and a Hopfion here, and you exchange them, you get precisely the same field configuration back. You're back at exactly the same point in CQ. Okay, so there's no way that the wave function can change sign when you do that. On the other hand, Finkelstein and Rubinstein realized if you have non-trivial topology, you could, instead of thinking of your wave function as being on the configuration space, think of it as being on the universal cover of the configuration space. And now, possibly, you can get fermionic quantization, because if in the two Hopfion configuration space, the loop which exchanges a pair of Hopfions is non-contractible and has order 2, then when you look in the universal cover, there are going to be at least 2 points corresponding to this configuration of a pair of Hopfions. And when you exchange them in the universal cover, that's not a, so in the configuration space, that's a closed curve, but in the universal cover, it's not a closed curve necessarily. Well, if it's non-contractible, it's not a closed curve, right? It's a path going from here to here or from here to here. Okay. So in this situation, you have the possibility of you define a wave function on this space. You could insist that its value here is minus its value here, and in that way, you can build in fermionic exchange statistics, even though all your fields are just scalar fields. Everything's bosonic. So you need the exchange loop to be non-contractible of even order, and there's a lot of consistency conditions which I won't go into. But the key question is, what is the fundamental group of the configuration space? So we're led to ask, what is the fundamental group of the space of maps from a compact-oriented 3-manifold into a 2-sphere? Okay? Okay, so how can we do that? Well, the tool we use, I didn't mention it, this is joint work with Stefan Krush. So the tool that we, meaning me and Stefan, used was the Hop vibration. Okay, so this is what it is. You think of the 3 spheres being the unit 3 sphere in C2. You map a pair of complex numbers in C2 to their projective equivalence class. So map from S3 to the CP1. And what this allows you to do is, if you're given a Skirm field, so that's a map from your domain into a 3 sphere, which you like to think of as being SU2 in fact, you can produce a map into the 2 sphere just by composing it with this vibration. Okay, so our idea was to think of this as a map from the Skirm configuration space, S3 to the M, to the Faddeev Skirm configuration space, S2 to the M. So it induces a map from this function space to this function space. Okay, why would we want to do that? What have we achieved? Why would we rather work with this thing than this thing? Well, 2 reasons. One is the Skirm model is old and venerable and well studied, so this space is quite well understood. For example, the Finkelstein-Rubinstein quantization has been well studied. And but the main the mathematical reason is that this is a group, so SU2 is a group, so this space of maps into SU2 is also a topological group, which gives you a lot of things for free. So, for example, every connected component is homeomorphic with every other one. The fundamental group must be abelian. All these things just follow immediately from this observation. So this is a nice space. This one we have no reason to expect is going to be anywhere near as nice as this space. Okay. So that's why we do it. So there's a basic fact, which is that this map, which we get by composing with the Fock vibration, is a surjection onto the algebraically essential maps, and it maps baryon number, i.e. topological degree, from M to S3 B to Hopf degree Q. Okay, so what can we use this thing for? Well, the essential observation about the Hopf vibration is that it is a vibration. So it has the homotopy lifting property, meaning if you have a map with respect to any domain X, so if you have a map from X to S2, and you have a lift of that map from X to S3, that's that up there, and you have a homotopy of this map from F0 to F1, then there exists a lift of the homotopy. In other words, you can complete this commutative diagram with this diagonal arrow, which you actually can't see very well. Okay? And this holds for all domains X. That's the definition of a vibration. Okay? Well, it's not very hard to take that and prove that the induced map into the space of maps from M into S3 and the space of maps from M into S2, algebraically essential, is a Serre vibration, which means it has this property but only with respect to all disks. Okay? So this thing is it's not quite a vibration, but it's a Serre vibration. And then the point is that if you're given any Serre vibration, so here we're thinking of this as being the map pi star, then it induces a long exact sequence in homotopy. Okay, so this is the total space. This is SU2 to the M. This is the base space, the space we're interested in, S2 to the M. This is the typical fiber, which if you think about it, is the map from M into U1, the fiber of the Hopf vibration. Okay, so we have this long exact sequence, so a chain of homomorphisms, where in each case the kernel of this one is exactly equal to the range of that one. Okay. Okay, so we have, by general nonsense, this long homotopy long exact sequence for these things, where this is the total space, base space, fiber, and then we can just think about what this map. So what about that map there? Well, this is given by inclusion of U1 into SU2. U1 contracts in SU2, so it's obvious that this map is trivial. Okay, so that goes to 0. And then you remember I told you it's nice when you're dealing with spaces of maps from M into a Lie group, because that's a topological group and you can do a lot of stuff. Well, so these things are nice. These spaces, this space and this space are very nice. You can understand them very well. You can actually compute what they are. So in the end, you can compute this thing and you find that you actually get a short exact sequence relating this thing you understand and this thing you want to understand and something else which you understand. First cohomology. Okay? So that's just that written as a corollary. Okay? And then in particular, if this is trivial, then this is an isomorphism. So in particular, if the fundamental group of M is finite, like if you're on a 3-sphere, then this map, which takes you from Skirm configurations to Hopf configurations, is an isomorphism on the fundamental groups. Okay. Okay. So what? So on S3 we know that these two fundamental groups are actually isomorphic, but we know more than that. We know an isomorphism between them, the one that you get by composing with the Hopf vibration. So we know that this group is Z2, and we know that it's generated by the image of the 2 Skirmion exchange loop, which is the 2 Fermionic, which is the 2 Hopfion exchange loop. So we know that that's non-contractible of order 2, which is the main condition we need for fermionic quantization. Okay? So I won't go through all that. You can go a lot further than this, and this is mainly what Stefan brought to the party, in fact. You can use the classical rotational and isorotational symmetries of the minimizers to impose symmetries on the parity of the wave function. From that, you can predict the spin and isospin quantum numbers of quantum ground states based on the symmetries of the classical energy minimizers. So by doing this and some very clever stuff, Stefan managed to come up with this table. So if you look for the quantum ground state of a given Hopf charge, just on symmetry grounds, in the fermionic quantization, we can predict its spin and isospin quantum numbers in this way. Okay, but I don't have time to say anything about that. Okay, so this is my final slide. Concluding remarks. We can do better than that. You can actually get energy spectrum within a collective coordinate approximation. It's slightly technical. but the punchline is that genuinely localized, i.e., algebraically essential Hopfions can be consistently fermionically quantized, and the way to understand that is to use the algebraic topology of the Hopf vibration. And at this point, I have to admit, this is all stuff I did in 2006. So I apologize for that. It's old, but it's still a classic, I think. And finally, I just want to advertise the fact that there are 2 jobs going in the maths department at Leeds. Thank you very much.
So, I mean, you might have answered that in your arrows and sequences, but in this Hopfion from Fermion ansatz,
Yes.
the Fermion level, you have a product ansatz, so you can multiply 2 U's, and that calculate the degree, and that is the sum of the 2 degrees.
Yes.
If you now project to these Hopfions, I mean, on the 2 sphere, you don't have a natural product structure. What is the relation between pi of U1 and pi of U2?
Pi.
Say pi means your composition map.
You're asking me what happens to the Hopf. You ask me what happens to the Hopf degrees.
But
they add the same as.
You have 2 Fermions, right?
Yes.
And you can multiply them, count the degree. Now you can project them to your Hopfions.
Yeah.
But there you're on the 2 sphere.
Yeah.
So there isn't really a natural product.
I agree, but you've just kind of defined one.
But yeah, but what does it? If you forget where it comes from, what does it mean in terms of this?
Oh, I see. As an actual. Oh, I see. As a. Well, I don't know. That's a good question. I mean, you have to. The thing is, it's not. You don't have a unique lift, right? So it's not like you can start off with a pair of maps into S2 and then define a product. Because you'd have to lift them, and what you get would depend on how you lift them, wouldn't it? So, yeah. I think the answer is there isn't really an unambiguous formula.
My question is related to this lift. I mean, you have a sequence of Hopfions from charge 1 up to charge 7. Do they come from particularly simple skyrmions?
No. So this precisely this map was used by Batty and Sutcliffe to try and generate interesting initial data for their minimization routines for the Fedorov-Hopf model. So they start off with things like stuff generated by the rational map ansatz, and then projected it using this, and uniformly it was terrible. It was nowhere near a solution. So this is certainly, you can't think of this as being a means of getting approximate Hopfions. That seems to be, except maybe for charge 1. It works for charge 1. But other than that, it's pretty hopeless. Or maybe charge 2 as well, actually. Maybe for axial symmetry. For axial symmetry, it works okay. You can take a rational map ansatz with z to the k, I think. But in general, no. It's a hopeless way of trying to get approximations to Hopfions.
But there's no unique lift of a
No.
Hopfion.
No, you have to make a choice.
So we have a very short coffee break. We were supposed to be back at 2:30, maybe 2:33 or something. Thank the speaker again.
Thank you.